Welcome back. Let's start to code our very first algorithm with breadthFirstSearch. If you remember, with breadthFirstSearch, we have to go from the top, then to the left, and then visit all the nodes in that level. And when I said that it uses a lot of memory, is that when it visits 6 and 12, from there, it's going to go back to 1, 4, then 34, then 45. So as it goes through this level, we need to keep a reference to all the children nodes of every node that we visit so that we can go back to them and visit 1 and 4. That's where the memory is coming from because we have to keep track of those children of the level that we're on. And you'll also notice this path that we're taking from 9 to 6 to 12 to 1 to 4 to 34, 45. We're going to be using a queue data structure, which allows us to keep a reference to the nodes that we want to come back to. Because we know 6 is in front of 12, we can go back to it and discover its child nodes. So let's get coding with our breadthFirstSearch algorithm. We have over here our binary search tree from our tree data structure section. We've already implemented the insert, lookup, remove methods, and we've created this binary search tree that gives us this type of tree. Let's remove these for now and start coding our own breadthFirstSearch implementation. And ideally, by calling this function, we get a list of all these items in the order of breadthFirstSearch. That is 9, 4, 20, 1, 6, 15, 1, 17. Let's call this breadthFirstSearch. And within here, we need 3 things. One is the current node, which will start with the root node. And we need 2 other things. One is the actual list that will be our answer. We'll have an array here where we insert these numbers into in the order of breadthFirstSearch. And we also need a queue data structure, which we'll use an array for this example, to keep track of the level we're at so that we can access the children once we go through it. Remember, we're going to keep track of 9, then we're going to keep track of 6 and 12. And when we get to 6 and 12, that's going to be in our queue, but we have to go back once we're at the end of that level to 6 so that we can discover 1 and 4. So that's what the queue will be used for. Now, the very first thing we're going to do is to add to the queue the very first item, the root node. So we're going to say queue.push current node. Now, what we need to do here is go from the current node down to our children node. And again, go from left to right, and then go to their children node and go from left to right. And the way we're going to do that is to use a while loop. And we'll say that as long as queue.length is going to be greater than 0, that is, we have nothing left in the queue. In that case, we'll say that the current node will be queue.shift. And shift simply means that we take the very first item in the queue. Remember, a queue is just a lineup to the roller coaster. And the first person that comes in gets to go first on the roller coaster. And shift simply returns and removes the first item in the queue. In our case, we'll have 9 as the first item in the queue, the 9 node. And we're going to shift that and assign it to the current node. And because this is the root node, we want to start off in our answer that the list will have the number 9 at the top. Let's move this up here just so you can see better. So the first thing we're going to do is say list.push the current node.value, which will be 9. So we have the first answer in our list, which is 9. From there, we're going to say, hey, does the 9 node have a left child? Because if it does, let's add it to the queue, saying that we need to check out that node, and we'll push it to the queue, current node.left. So what we just did here is we've added 4 to the queue. And then we also want to add 20 to the queue. So I'm going to say if, after you've added 4 to the queue, I'm going to say, hey, does the current node have a right node, child node? in that case, we'll add it to the queue again as the second item in the queue, and the current node dot right will be pushed to the queue. And this is the amazing thing of what we just did. Now that the queue has 2 items, as it passes through, it'll have 4 and 20. It's going to loop through, come to this line and say queue.shift is going to grab 4 and say push 4 to the list. And then it's going to say, hey, does 4 have a left child? Yes, it does. It has 1. Well, then add it to the queue. So 1 gets added to the queue that has 4, 20, and now 1. And then we say, hey, does 4 have a right child? Yes, we have 6. Well, we're going to add that to the queue again. So we're going to have 4, 20, 1, 6. And then we go back to the top and say, what's next in line? Well, we have 20. So let's shift 20, grab that, remove that from our queue, and go through it again. Again, left child will be 15, and right child will be 170. If we console.log here, our current node dot value, and actually let's just log it down here, which will be the shifted node. That is the node that we're going to be operating on and checking. Oh, and we'll have to actually call that. So let's do tree.breadthFirstSearch, and I click run. We see that I'm checking 9, then I'm checking 4, then I'm checking 20, then I'm checking 1, then 6, then 15, then 170. Very, very cool. And we're pushing that to the list every time. So all we need to do at the end is just say return list. So that if I run this, look at that. I have my breadthFirstSearch that returns 9, then 4, then 20, then 1, 6, 15, and 170. That wasn't too bad, was it? We see from this code here that it's quite simple. And the only issue that we have is that this queue can get pretty large because we have to keep reference to our child nodes. The memory consumption that can really hurt us is this queue that we keep adding to. We keep popping things, but we also add to the queue. So that if we have a really wide tree, instead of a binary tree where we just have a left and a right, and maybe we have 10 child nodes, this queue can get pretty big. And depending on the data, that memory consumption might be big. And that's one of the main downside with breadthFirstSearch. But hopefully you see the simplicity of breadthFirstSearch. Wasn't too bad, was it? All right, I'll see you in the next video. Bye-bye.